An intermodal container is a large standardized shipping container, designed and built for intermodal freight transport, meaning these containers can be used across different modes of transport, from ship to rail to truck, without unloading and reloading their cargo. Intermodal containers are primarily used to store and transport materials and products efficiently and securely in the global containerized intermodal freight transport system, but smaller numbers are in regional use as well. These containers are known under a number of names, such as simply container, cargo, a freight container, ISO container, shipping, sea or ocean container, container van, a box, CSE can. Intermodal containers exist in many types and a number of standardized sizes, but 90% of the global container fleet is called dry freight or general-purpose containers, durable closed steel boxes, mostly of either 20 or 40-foot standard length. The common heights are 8 feet 6 inches and 9 feet 6 inches. The latter are known as high cube or high cube containers. Just like cardboard boxes and pallets, these containers are a means to bundle cargo and goods into larger, unitized loads that can be easily handled, moved, and stacked, and that will pack tightly in a shipyard. Intermodal containers share a number of key construction features to withstand the stresses of intermodal shipping, to facilitate the handling and to allow stacking, as well as being identifiable through their individual, unique ISO 6346 reporting mark. In 2012 there were about 20.5 million intermodal containers in the world of varying types to suit different cargoes. Containers have largely supplanted the traditional breakbulk cargo. In 2010 containers accounted for 60% of the world's seaborne trade. The predominant alternative methods of transport carry bulk cargo, either gaseous, liquid or solid, e.g., by bulk carrier, a tank ship, tank car, a truck. For air freight, the more lightweight IATA-defined unit load device is used. History. By the 1830s, railways on several continents were carrying containers that could be transferred to other modes of transport. The Liverpool and Manchester Railway in the United Kingdom was one of these. Simple rectangular timber boxes, 4 to a truck, they were used to convey coal from the Lancashire collieries to Liverpool, where they were transferred to horse-drawn carts by crane. Early versions of standardized containers were used in Europe before World War II. Construction of these containers had a steel frame with wooden walls, floor, roof and doors. The first international standard for containers was established by the Bureau International des Containers et du Transport Intermodal in 1933, and a second one in 1935, primarily for transport between European countries. American containers at this time were not standardized, and these early containers were not yet stackable, neither in the U.S. nor Europe. In November 1932, the first container terminal in the world was opened by the Pennsylvania Railroad Company in Andola, PA. The development of containerization was created in Europe and the US as a way to revitalize rail companies after the Wall Street crash of 1929 in New York, and resulting economic collapse and drop in all modes of transport. In April 1951 at Zurich Tiefenbrunnen railway station, the Swiss Museum of Transport and the Bureau International des Containers held demonstrations of container systems for representatives from a number of European countries, and from the United States. A system was selected for Western Europe, based on the Netherlands system for consumer goods and waste transportation called Laadkisten, in use since 1934. This system used roller containers for transport by rail, truck and ship, in various configurations up to 5,500 kilograms capacity, and up to 3.1 by 2.3 times 2 meters in size. This became the first post-World War II European railway standard of the International Union of Railways (UIC 590), known as Paarbehalte. It was implemented in the Netherlands, Belgium, Luxembourg, West Germany, Switzerland, Sweden and Denmark. The use of standardized steel shipping containers began during the late 1940s and early 1950s, when commercial shipping operators and the U.S. military started developing such units. In 1948, the U.S. Army Transportation Corps developed the Transporter, a rigid corrugated steel container able to carry 9,000 pounds. It was 8 feet 6 in long, 6 feet 3 in wide, and 6 feet 10 in high, with double doors on one end, was mounted on skids, and had lifting rings on the top 4 corners. After proving successful in Korea, the Transporter was developed into the Container Express box system in late 1952. Based on the Transporter, the size and capacity of the Connex were about the same, but the system was made modular by the addition of a smaller, half-size unit of 6 feet 3 in long, 4 feet 3 in wide and 6 feet 10.5 in high. Connexes could be stacked 3 high, and protected the contents from the elements. By 1965, the U.S. military used some 100,000 Connex boxes, and more than 200,000 in 1967, making this the first worldwide application of intermodal containers. From 1949 onwards, engineer Keith Tantlinger repeatedly contributed to the development of containers, as well as the handling and transportation equipment. In 1949, while at Brown Trailers Inc. of Spokane, he modified the design of the stress-skin aluminum 30-foot trailer to fulfill an order of 230 by 8 by 8.5 feet containers that could be stacked 2 high for Alaska-based ocean van lines. Steel castings on the top corners provided lifting and securing points. In 1955, trucking magnate Malcolm McLean bought Pan Atlantic Steamship Company to form a container shipping enterprise, later known as Sealand. The first containers were supplied by Brown, where McLean met Keith Tantlinger and hired him as Vice President of Engineering and Research. Under the supervision of Tantlinger, a new 35 feet by 8 feet by 8 feet 6 in Sealand container was developed, the length determined by the maximum length of trailers then allowed on Pennsylvanian highways. Each container had a frame with 8 corner castings that could withstand stacking loads. Tantlinger also designed automatic spreaders for handling the containers, as well as the twist lock mechanism that connects with the corner castings. 2 years after McLean's first container ship, the Ideal X started container shipping on the U.S. East Coast. Matson Navigation followed suit between California and Hawaii. Just like Pan Atlantic's containers, Matson's were 8 feet wide and 8 feet 6 in high, but due to California's different traffic code, Matson chose to make theirs 24 feet long. In 1968, McLean began container service to South Vietnam for the U.S. military with great success. ISO standards for containers were published between 1968 and 1970 by the International Maritime Organization. These standards allow for more consistent loading, transporting, and unloading of goods in ports throughout the world, thus saving time and resources. The International Convention for Safe Containers is a 1972 regulation by the Intergovernmental Maritime Consultative Organization on the safe handling and transport of containers. It decrees that every container traveling internationally be fitted with a CSC safety approval plate. This holds essential information about the container, including age, registration number, dimensions and weights, as well as its strength and maximum stacking capability. Longshoremen and related unions around the world struggled with this revolution in shipping goods. For example, by 1971 a clause in the International Longshoremen's Association contract stipulated that the work of stuffing or stripping a container within 50 miles of a port must be done by ELA workers, or if not done by ELA, that the shipper needed to pay royalties and penalties to the ELA. Unions for truckers and consolidators argued that the ELA rules were not valid work preservation clauses because the work of stuffing and stripping containers away from the pier had not traditionally been done by ELA members. In 1980, the Supreme Court of the United States heard this case and ruled against the ELA. Description: 90% of the global container fleet consists of dry freight or general-purpose containers, both of standard and special sizes, and although lengths of containers vary from 8 to 56 feet, according to two 2012 container census reports, about 80% of the world's containers are either 20 or 40-foot standard-length boxes of the dry freight design. These typical containers are rectangular, closed-box models, with doors fitted at one end, and made of corrugated weathering steel with a plywood floor. Although corrugating the sheet metal used for the sides and roof contributes significantly to the container's rigidity and stacking strength, just like in corrugated iron or in cardboard boxes, the corrugated sides cause aerodynamic drag, and up to 10% fuel economy loss in road or rail transport, compared to smooth-sided vans. Standard containers are 8 foot wide by 8 feet 6 in high, although the taller high cube or high cube units measuring 9 feet 6 inches have become very common in recent years. By the end of 2013, high cube 40 feet containers represented almost 50% of the world's maritime container fleet. According to Drewry's Container Census report, about 90% of the world's containers are either nominal 20-foot or 40-foot long, although the United States and Canada also use longer units of 45 feet, 48 feet and 53 feet. ISO containers have castings with openings for twist-lock fasteners at each of the 8 corners to allow gripping the box from above, below, or the side, and they can be stacked up to 10 units high. Regional intermodal containers, such as European and U.S. domestic units, however, are mainly transported by road and rail, and can frequently only be stacked up to 3 laden units high. Although the two ends are quite rigid, containers flex somewhat during transport. Container capacity is often expressed in 20-foot equivalent units. A 20-foot equivalent unit is a measure of containerized cargo capacity equal to one standard 20-foot long container. This is an approximate measure wherein the height of the box is not considered. For example, the 9 feet 6 in tall high cube, as well as 4 foot 3 inch half-height 20-foot containers are equally counted as 1 TEU. Similarly, extra-long 45 feet containers are commonly designated as 2 TEU, no different than standard 40 feet long units. 2 TEU are equivalent to 1 40-foot equivalent unit. In 2014, the global container fleet grew to a volume of 36.6 million TEU, based on Drewry Shipping Consultants' container census. Moreover, in 2014, for the first time in history, 40-foot high cube containers accounted for the majority of boxes in service, measured in TEU. Manufacturing prices for regular dry freight containers are typically in the range of $1,750, $2,000 US per CEU, and about 90% of the world's containers are made in China. The average age of the global container fleet was a little over 5 years from end 1994 to end 2009, meaning containers remain in shipping use for well over 10 years. Types other than the standard, general-purpose container. Many variations exist for use with different cargoes. The most prominent of these are refrigerated containers for perishable goods, that make up 6% of the world's shipping boxes, and tanks in a frame, for bulk liquids, account for another 0.75% of the global container fleet. Although these variations are not of the standard type, they mostly are ISO standard containers. In fact, the ISO 6346 standard classifies a broad spectrum of container types in great detail. Aside from different size options, the most important container types are general-purpose dry vans, for boxes, cartons, cases, sacks, bales, pallets, drums, etc. Special interior layouts are known, such as rolling floor containers, for difficult-to-handle cargo garmentainerers, for shipping garments on hangers. Ventilated containers, essentially dry vans, but either passively or actively ventilated. For instance, for organic products requiring ventilation, temperature-controlled, either insulated, refrigerated and/or heated containers, for perishable goods. Tank containers, for liquids or gases. Frequently these are dangerous goods, and in the case of gases, one shipping unit may contain multiple gas bottles. Bulk containers, either closed models with roof lids, or harder soft open-top units for top loading, for instance for bulk minerals. Containerized coal carriers and inliners are used in Europe. Open-top and open-side containers, for instance for easy loading of heavy machinery or oversized pallets. Open sides are also used for ventilating hardy perishables like apples or potatoes. Platform-based containers such as flat rack and bolster containers, for barrels, drums, crates, and any heavier bulky out-of-gauge cargo, like machinery. Semi-finished goods or processed timber. Empty flat racks can either be stacked or shipped sideways in another ISO container. Collapsible containers, ranging from flush folding flat racks to fully closed ISO and CSC certified units with roof and walls when erected. Containers for offshore use have a few different features, like pad eyes, and must meet additional strength and design requirements. Standards and certification, such as the DNV 2.7-1 by Det Norsk Veritas and the European Standard EN 12079, offshore containers and associated lifting sets. A multitude of equipment, such as generators, has been installed in containers of different types to simplify logistics. See containerized equipment for more details. Swap body units usually have the same bottom corner fixtures as intermodal containers, and often have folding legs under the frame so that they can be moved between trucks without using a crane. However, they frequently don't have the upper corner fittings of ISO containers, and are not stackable, nor can they be lifted and handled by the usual equipment like reach stackers or straddle carriers. They are generally more expensive to procure. Specifications. Basic dimensions and permissible gross weights of intermodal containers are largely determined by two ISO standards. ISO 668-2013 Series 1 Freight Containers, Classification, Dimensions and Ratings. ISO 1496-1-2013 Series 1 Freight Containers, Specification and Testing, Part 1, General Cargo cargo containers for general purposes. Weights and dimensions of the most common standardized types of containers are given below. The values vary slightly from manufacturer to manufacturer, but must stay within the tolerances dictated by the standards. Empty weight is not determined by the standards, but by the container's construction, and is therefore indicative, but necessarily to calculate a net load figure by subtracting it from the maximum permitted gross weight. Stacking containers. At stacking load-bearing locations, 40-foot containers of the standard unit length, and 45 feet, 48 feet, and 53 feet all stack at the 40 feet coupling width. Other units can be stacked on top of 20 feet units only if there are two in a row, but 20 feet units cannot be stacked on top of 40 feet units, or any other large container. The coupling holes are all female, and it takes a double male twist lock to securely mate stacked containers together. Non-standard and uncommon sizes. Pallet-wide containers. Pallet-wide containers have about 4 inches more internal floor width than standard containers to accommodate more Euro pallets, common in Europe. These containers typically have an internal width of 2.44 meters, to be able to load either 2 or 3 of the 1.2 meters long by 0.8 meters wide pallets side by side. Many sea shipping providers in Europe allow these as overhangs on standard containers are sufficient and they fit in the usual interlock spaces. Especially the 45 feet pallet wide high cube short sea container has gained wider acceptance, as these containers can replace the 13.6 meters swap bodies that are common for truck transport in Europe. The EU has started a standardization for pallet-wide containerization in the European Intermodal Loading Unit Initiative. Australian race containers are also slightly wider to optimize them for the use of Australia's standard pallets. 48-foot containers. The 48-foot shipping container is a high cube container in that it is 9 feet 6 in tall on the exterior. It is 8 feet 6 in wide, which makes it 6 inches wider than ISO standard containers. This size was introduced by container shipping company APL in 1986, and is used domestically in North America on road and rail, and may be transported on deck by ship. This size, being 8 feet longer and 6 inches wider, has 29% more cubic capacity than the standard 40 feet high cube, yet the cost to move it by truck or rail are almost the same. 53-foot containers. General purpose 53-foot containers were introduced in the United States in 1989, and are used both in the USA and Canada, mainly for domestic road and rail transport. They are considered high cubes based on the 9 feet 6 in ISO standard height. The width of 8 feet 6 in, however, makes them 6 inches wider than ISO standard containers. These large boxes have 60% more capacity than standard height 40-foot containers, enabling shippers to consolidate more cargo into fewer containers. Generally, North American 53-foot containers were not constructed strongly enough to endure the rigors of ocean transport, but in 2007 container carrier APL introduced the first 53-foot ocean-capable containers. All new, reinforced 53-foot boxes were built specifically for international trade and designed to withstand ocean voyages on its South China to Los Angeles service. In 2013, however, APL stopped offering vessel space for 53-foot containers on its trans-Pacific ships. Nevertheless, in 2015 both Crowley and Tote Maritime each announced the construction of the respective second combined container and AMP RoRo ships for Puerto Rico trade, with a specific design to maximize cubic cargo capacity by carrying 53-foot 102-inch inch wide containers. Within Canada, OceanX offers 53-foot container ocean service to and from the island of Newfoundland. 53-foot containers are also being used on some Asia-Pacific international shipping routes. Small containers. The United States military continues to use small containers, strongly reminiscent of the transporter and Connex boxes of the 1950s and 1960s. These either comply with ISO standard dimensions or are a direct derivative thereof. Current terminology of the U.S. Armed Forces calls these small containers bicon, tricon and quadcon, which correspond with ISO 668 standard sizes 1D, 1E and 1F respectively. This comes down to containers of 8 feet height, and with a footprint size either 1/2, 1/3 or 1/4 the size of a standard 20-foot, 1 TEU container. At a nominal length of 10 feet, 2 bicons coupled together lengthwise match one 20-foot ISO container, but the height is 6 inches shy of the more commonly available 10-foot ISO containers of so-called standard height, which are 8 feet 6 in tall. Tricons and quadcons, however, have to be coupled transversely, either 3 or 4 in a row, to be stackable with 20-foot containers. The length of 8 feet corresponds to the width of a standard 20-foot container, which is why there are forklift pockets at their ends, as well as in the sides of these boxes, and the doors only have one locking bar each. The smallest of these, the quadcon, exists in 2 heights, 96 in or 82 in. Only the first conforms to ISO 668 standard dimensions. Reporting mark. Each container is allocated a standardized ISO 6346 reporting mark, 4 letters long ending in either U, J or Z, followed by 6 digits and a check digit. The ownership code for intermodal containers is issued by the Bureau International des Containers in France, hence the name BIC code for the intermodal container reporting mark. So far there exist only 4-letter BIC codes ending in U. The placement and registration of BIC codes is standardized by the Commission's TC 104 and TC 122 in the JTC 1 of the ISO, which are dominated by shipping companies. Shipping containers are labeled with a series of identification codes that includes the manufacturer code, the ownership code, usage classification code, UN placard for hazardous goods, and reference codes for additional transport control and security. Following the extended usage of pallet-wide containers in Europe, the EU had started the Intermodal Loading Unit initiative. This showed advantages for intermodal transport of containers and swap bodies. This led to the introduction of ILU codes defined by the standard N 13044, which has the same format as the earlier BIC codes. The International Container Office BIC agreed to only issue ownership codes ending with U, J or Z. The new Allocation Office of the UIR agreed to only issue ownership reporting marks for swap bodies ending with A, B, C, D or K. Companies having a BIC code ending with U can allocate an ILU code ending with K having the same preceding letters. Since July 2011, the new ILU codes can be registered. Beginning with July 2014, all intermodal ISO containers and intermodal swap bodies must have an ownership code, and by July 2019 all of them must bear a standard conforming placard. Handling. Containers are transferred between rail, truck, and ship by container cranes at container terminals. Forklifts, reach stackers, straddle carriers, and cranes may be used to load and unload trucks at trains outside of container terminals. swap bodies, side lifters, tilt deck trucks, and hook trucks allow transfer to and from trucks with no extra equipment. ISO standard containers can be handled and lifted in a variety of ways by the corner fixtures, but the structure and strength of 45-foot containers limits the tolerance of side lifting, nor can they be forklifted based on ISO 3874. Transport. Containers can be transported by container ship, truck and freight trains as part of a single journey without unpacking. Units can be secured in transit using twist lock points located at each corner of the container. Every container has a unique bit code painted on the outside for identification and tracking, and is capable of carrying up to 20 to 25 metric tons. Costs for transport are calculated in 20-foot equivalent units. Rail. When carried by rail, containers may be carried on flat cars or well cars, the latter especially designed for container transport and can accommodate double-stacked containers. However, the loading gauge of a rail system may restrict the modes and types of container shipment. The smaller loading gauges often found in European railroads will only accommodate single-stacked containers. In some countries, such as the United Kingdom, there are sections of the rail network through which high-cube containers cannot pass, or can pass through only on well cars. On the other hand, Indian Railways runs double-stacked containers on flat cars under 25 kV overhead electrical wires. The wires must be at least 7.45 meters above the track, but ION is able to do so because of its large loading gauge and the extra stability provided by its 1,676 mm track. China Railways also runs double-stacked containers under overhead wires, but must use well cars to do so. Since the wires are only 6.6 meters above the track and 1,435 mm does not provide adequate stability to run double-stacked containers on flat cars. About 90% of non-bulk cargo worldwide is transported by container, and the largest container ships can carry over 19,000 TEU. Each year an estimated 10,000 shipping containers fall into the sea. Of these, 10% are expected to contain chemicals toxic to marine life. Plane containers can also be transported in planes, as seen within intermodal freight transport. However, transporting containers in this way is typically avoided due to the cost of doing such and the lack of availability of planes which can accommodate such awkwardly sized cargo.